Hello everyone, my name is Oindrila. I'm a fourth year PhD student in environmental engineering at the University of Maryland, Baltimore County, working with Dr. Upal Ghosh. In this presentation, I will go over a part of my work on the testing of prototypes of actively shaken in situ passive sampler platform for polychlorinated biphenyls. This work is in collaboration with Dr. Mehergan Jalalizadeh, who was a former PhD student in Dr. Ghosh's lab and is currently a senior associate at Exponent. She was the one who started working on this project originally and built and tested some of the earliest prototypes. In fact, in this work, we will use one of the prototypes she and her colleagues built while she was working as a senior staff engineer at Geosyntec. This seed project is funded by SERDP. Passive sampling provides an important estimate of the freely dissolved concentration of a hydrophobic organic contaminant in the environment, which is a very useful metric of the contaminant's bioavailability to the aquatic organisms. The use of passive sampling avoids the need to collect large volumes of environmental substrates. To sample these HOCs, which exist in the environment in very low but fatal amounts of the order of nanogram or picogram per liter, and yet meet the detection limits of the gas chromatographic instruments that we use to quantify them. Many of these organics that have a varied range of hydrophobicity often do not come to equilibrium in practical deployment times of days, weeks, or months. So we use performance reference compounds to correct for the non equilibrium conditions. The HOC we are dealing with in this study is polychlorinated biphenyls, PCBs. Mass transfer uptake kinetics of more hydrophobic PCBs like PCB 100 in sediment pore water is slower than less hydrophobic compound like PCB4 as is represented in this diagram. Thus, the larger, more hydrophobic compounds need more PRC correction. The errors involved in calculating the PRC correction term is further propagated into the freely dissolved concentration measurements. In this context, we propose to develop a passive sampling platform that introduces periodic vibration for faster uptake of more hydrophobic compounds like higher homolog PCBs, dioxins, or furans. The vibration essentially breaks the water boundary layer, which is close to the passive sampler, and speeds up the mass transfer for faster approach to equilibrium for truer representation of the pore water concentration. Over the course of this project, we have built many prototypes and are still in the process of optimizing the design components, scale, and operating frequency of these to suit our needs. Prototype P1 was modified from the Vibra SP3 device built by Meg at Geosyntec by changing the way the PE sheet was placed, hoping if we spread them out on the side instead of attaching it to the back of the aluminum box, it will increase the exposed surface area at the same time maintaining maximum possible contact with the vibrating aluminum body. Prototype P2 was built as two devices with a bigger and stronger motor of 110 G normal amplitude, and we went back to the former design of MIGs where the cylindrical vibrating unit is separate from the power unit because the vibration was better distributed and strongly felt on the fins. The first device was built by Lewis, who joined our lab as an undergrad student and is still working with us, helping me building and working my way around these prototypes as a general assistant. The second device, I was able to put it together with the help of the UMBC Machining, Microfabrication, and Electronics Technical Service Center. This device was designed to hold a 3-axis vibration data logger. With this, we could check the end at the end of our deployment if the device had vibrated all along. Now, device 1 can accommodate zero point 0.4 grams of 2 mil PE in each of the three wings, and so a total of 1.2 grams of PE. Device 2, on the other hand, can accommodate 2.8 grams of 2 mil PE in total. We ran several leak checks on our prototypes in the lab before we took them out to the field on 10th December 2019 for the first time, which was before the lockdown. Deployed them for 10 days at Kingman Lake in Washington, D.C. We also did in lab experiments where we mixed a big batch of sediment from several sites in a plastic container about 3 feet in diameter and 4 feet deep. We homogenized the sediment with water using a giant propeller attached at the end of a drilling equipment and deployed the vibrating prototypes in this tub, leaving about a foot distance between each device and about half a foot distance from the sides. We scooped out a part of the homogenized sediment into a 2-liter glass beaker where we deployed our static samplers and another part into a jar with a lid for our fully mixed scenario to put it on the roller. So, for our final and most recent experiments, the results of which we present here, we used polyethylene sheets of 1 mil thickness loaded with C13 PRCs, and we used a vibration frequency of 5 seconds pulse after every 1 hour pause. After our field test, the data from the vibration data logger showed that our device had vibrated for all the 10 days of deployment with an average G force of 2.5 inside 3 inch of the sediment. And we could not make sense of the PCB target analyte uptake or PRC loss data from our field test, unfortunately, because the deployment period was quite short and the lake was frozen at that time of the year, which led to very slow mass transfer. Post pandemic lockdown, we did several lab experiments where we ran into a series of problems of uneven PRC loading in our samplers, optimizing the design of our devices for more robustness until we were more confident. And we also made the wise choice of shifting from non labeled C12 PRCs to labeled C13 PRCs because the higher PCB analyte uptake in the vibrating prototypes would often mask the little chromatogram peaks of the PRCs, which would become increasingly difficult to account for. So, after spending a good amount of 6 to 8 months of fixing these issues, we were finally able to run a batch of successful experiments. We used 6 C13 PRCs in total, but ended up using 4 of them for our final estimations. After 7 days, the static sampler has lost around 38% of the Tetra PRC54, P1 around 50%, while P2 with the most powerful motor has lost around 59% of PRC54. So the percentage loss rate is much faster in the vibrating prototypes than the static samplers. But as the hydrophobicity of the PRCs increase, the gap between the percent loss for the static and the vibrating prototypes reduces. After 14 days, we see that the percent loss values have increased for all the PRCs from after 7 days, and the static sampler has almost caught up with the percent loss values for hexa and hepta PRCs in the vibrating prototype P1. P2, however, has been losing PRCs all the way because of the more intense vibration. Achieving around more than 10% loss may be sufficient to perform PRC calculations and estimate pore water concentrations. So we do see promising results, but we are working on making this even better. Here we are looking at the mass of PCBs accumulated in passive sampling prototypes normalized by the mass of polymer in each of them after 7 and 14 days. The tri and tetra are the most abundant homologs. In most cases, the vibrating prototypes, represented by the red and green bars, have more accumulated PCBs in the polymer. At the end of 14 days, the static, which is represented by the blue bars, is slowly catching up with the P1 prototype represented by the red bars, at least for the tri, tetra, and penta homologs. The P2 levels are still quite high, which is good. The fully mixed scenario, the purple bars that you see there, is picking up less than anticipated. This could be because of less amount of water used to make the slurry. The equilibrium passive sampling concentrations were calculated by correcting these values by the PRC loss data, and the fraction of equilibrium reached calculated as the ratio of the actual and the equilibrium passive sampler concentrations. So this graph here shows the fractional approach to equilibrium of total PCBs as a function of time for all the static and vibrating prototypes. We see that the vibrating prototypes are approaching equilibrium faster than the static, and this is because of the periodic vibration which is breaking the water boundary layer close to the passive sampler and enhancing mass transfer. The fully mixed scenario is closest to the equilibrium, but we were anticipating even faster kinetics, but probably that is not the case because of less flow in the system. We see that at the end of 14 days, the static sampler has almost caught up with prototype P1. P2 is still performing slightly better because of the stronger motor. When we bar plot the fractional equilibrium of each homologue for static versus prototype P2, there is a substantial difference created by the vibration for the higher homologue groups. For example, if you see at the end of 7 days, the vibration in P2 has helped the hepta group reach equilibrium 4 times closer than static and almost 7 times closer to equilibrium for octa, which is a great improvement. So overall, introducing periodic vibration to the passive sampling platforms did improve mass transfer because the water boundary layer is disrupted by introducing turbulence artificially. When the vibration frequency is kept constant, we did see that a stronger vibration with a bigger motor did help in approaching equilibrium faster. Also, the larger prototypes could accommodate more polyethylene in them. There was a big improvement in the rate of approaching equilibrium for the higher homologue series when the vibration is introduced, especially for hexa to octa. And a more frequent but short lived vibration might improve the rate of equilibrium even further. We might also want to decrease how far the fins extend out, and this would increase the effectiveness of vibration. I would like to thank everyone associated with this project, starting from SERDIP for funding this project, Dr. Ghosh, my advisor, Meg, who was the one who started working on this project to start with and has shared some valuable advice from time to time, all the Ghosh Lab members, and especially Louis for helping me build this prototype from scratch, Chris from Geosyntec for helping me understand and debug the Arduino microcontroller code used in the prototype. Thank you, everyone. And with that, I can take any questions you might have for me.